Okay, so now we're up to the final step here in our analysis, which is getting the equation and including uncertainties in our equation. So we can write the equation for each of these three lines down here. So the equation for our line of best fit is, and then I'm going to go to the insert drop-down menu and choose equation. And I'm going to write here y equals mx plus c, except our y value is speed, so I'm going to write v is equal to, and the gradient of our line of best fit is 9.087 times, and our x variable is the square root of radius, so I'm going to write backslash sqrt space, and I'm going to put r in here. And then we want to go plus the y-intercept, but in this case the y-intercept is negative 1.388, so I'm going to go minus 1.388. That's the equation for our line of best fit. I'll make my equation centered. Okay, and then the equation for the max gradient error line is, and we'll write that one down too. And we'll go insert equation. And in fact, I'm not going to bother. I'm going to take this one and just copy it. And I'm going to change the numbers. So the max gradient one is the red one. So it's 14.02. And the y-intercept for the red one is negative 4.245. So there's our max gradient error line. And then the equation for the min gradient error line. And I'm going to paste that same one again, but this time I'm going to get the blue one, which was 5.973 and positive 0.4810. 5.973. And then we had, this one was plus 0.4810. So all of these equations are just y equals mx plus c, except our y variable is speed and our x variable is square root of r. Okay, so now the uncertainty in gradient is just, we can insert equation here. So we can call that delta m equals, and that's the max gradient minus the min gradient over 2. So I'm going to write it like this. So backslash, and if I write frac, it gives me a fraction. And then I'm going to write 14.02 minus 5.973 divided by 2. That's half the range of the gradients. That's my uncertainty in the gradient. So let me do that. 14.02 minus 5.973 equals, and then divide that by 2. We get 4.02. Okay, and then we do the same for the y-intercept. Let's just center all of our equations here. And for this one, I can just copy because it's going to be the same format. So this is delta b or c or whatever we like to use. Here it uses b for y-intercept, so I'm going to say delta b. And the biggest y-intercept was 0.4810. So we just choose the biggest one and put that one first. And then we go choose the smallest one, which was the red one, which was negative 4.245. So it's minus negative it was negative 4.245. over 2, and that's not going to be equal to this. So let's find out what that is. 0.4810 minus, what was it? Let me just move my calculator here. 4.245. So minus 4.245, and that was negative. So that's equal to 4.726. Note that we won't all agree on exactly what these values are, but they're going to be very similar for all of us. We won't agree because we would all have dragged these lines slightly differently. Okay? So now the last step is to write our equation with uncertainties. So I'm going to put our best fit line, I'm going to copy that and write it in here. So the final equation for our relationship is, so that's our line, that's our best estimate of the gradient, and then we want to go /PM to get a plus minus, and then we want the uncertainty in the greatest, which is 4.02. However, we only need 2 significant figures for that, which means we have to round this one to the same number of decimal places. So it's 9.1 plus or minus 4.0 times the square root of radius, and then minus 1.388, and then we want plus or minus the uncertainty in our y-intercept, which was 4.726, so 4.7, and then this should be to the same number of decimal places, so 1.4 plus or minus 4.7. Okay, so here is our equation for our line, including our uncertainties. So I'm going to just, because I'm so proud of this equation, I'm going to make it a little bit bigger. Okay, so that gives us the equation. Now, the next little thing that we can do here is just go back and add sample calculations to the things that we had to calculate. So if we have a look at our data table here, we should show our reader how we worked all these things out. So the uncertainty in the, this is a heading, let's change that back to normal. So the uncertainty in the radius was estimated to be 0.02 meters because there was some movement of the string. And then the average was just the sum of our 5 trials divided by 5. The uncertainty of the average was half of the range in the 5 trials. And the uncertainty in the speed, the uncertainty was propagated for the speed, and that's the only one that's really complicated enough to warrant showing how it worked. So I'm going to go insert equation. In fact, I'm just going to say, yeah, in fact, I will insert equation here. I'll go, for example, in the first row, for the speed in the first row, we simply divided, and I'll insert equation 2 pi r by t. And I'll insert equation. So 2 times pi spacebar times, and the radius was 0.15. In fact, I'm going to put this all in a fraction like this. frac over the period in the first row was 0.439, and that gave us the speed, which was 2.15 meters per second, and the uncertainty was propagated by adding the relative uncertainties in the radius and the period, and then converting back to an absolute uncertainty. So I'll go insert equation, and then I will take the relative uncertainty. So that was frac 0.02 over 0.15 plus, and then we had the relative uncertainty in the period, so that was 0.050 over 0.439, and then we'll put brackets around that. Just go all the way back to here, and then hit spacebar, and then times, and then the speed, which is 2.15, and that gave us 0.53. Okay, those are the only two that really required a calculation in that first row. Okay, and then we also had to do the propagation here. So the to find the square root of the radius, we did the following. Insert equation, square root, the first value was 0.15 equals 0.39, and to propagate its uncertainty, we just multiplied the relative uncertainty by 0.5 and converted back to an absolute uncertainty. So that was insert equation, and it was 0.02 frac 0.02 over 0.15 times 0.5 times 0.39, which gives us 0.03. Okay, so now we've shown all of our calculations. The last step we'll do together in class. If you can aim to get yourself up to this point as soon as possible, you can always use the video to review how to do this as well when you're doing it in the future.